Introduce Professor Ting Xu. She received her master's from polymer physics from the Chinese Academy of Science in 1999 and a PhD from the University of Massachusetts in 2004. She was a postdoc at UPenn, and she was at NIST before she joined Berkeley here in January 2007. She is a professor in materials science and engineering and also in the Department of Chemistry. She's going to talk to us today about assembled styrofoam for nanodevices. So let's give her a nice warm welcome, please.
All right, so good afternoon, and thank you everyone for taking your lunch break and come here, and hopefully I'm going to tell you a little bit work we do related to nanostructured polymeric materials. Okay, so as discussed, I'm an assistant professor at the Material Science and the Chemistry Department, and also as a part of Material Science Division at the Lawrence Berkeley National Lab. And my group is a polymer group, and we mainly focus on trying to control the nanostructure and using polymer as a structure frame and trying to generate functional materials. So when we talk about polymers, I always like to show this slide, and many of you probably watched the movie The Graduate, and there's one segment says dialogue in it's basically just one word, and that word is plastics. And that was fairly early on, and now plastics is still going on very strong, and we start to move from the commodity product into a sort of like a high tech nanostructured materials thing, trying to help out the development of nanotechnology. I'm going to show you some of the work with nanostructured polymers. So just a general idea to see how great polymers are and that they're used in our daily life. And you can see that if you ride a car and go to the food court, or if you're interested in the fashion industry. And of course, a lot of us are surrounded with styrofoam, whether you drink coffee or open up packages, etc. Okay, and from the natural polymeric materials aspect, you can see silk, has a very great, properties, and actually it has been years people trying to mimic the property you see in silk, and it has not been very successful. And rubber tree, that's, you have the rubber, natural rubber, and that's where a lot of polymer science actually started. And if you look at ourselves, you'll see that without DNA, we probably wouldn't be who we are. And of course, without proteins, which most of us are made of, and you probably wouldn't be where we are either. So what I'm going to tell you today is what are the simplest polymer you can think about. Styrene, polystyrene can be applicable if the minute you start to control the nanostructures. Okay, so what is the styrofoam? Styrofoam here is a chemical structure of the styrofoam you have in there. Okay, and each individual unit they called styrene. Okay, so when we link them together hand in hand, we call them, you get a polymer which is polystyrene, and the abbreviation is a PS. Okay, and if you, through the extrusion, while trying to get the melt, start to go out, and you just blow a little bit of air in there, and you are going to generate a styrofoam. Okay, so polystyrene plus air is your styrofoam. So what can the styrofoam be good for nanotechnology? Okay, so we'll just play a little bit trick. So this is a chemical structure I just introduced in last slide. That's a styrene. Okay, and if you covalent link with another polymer, in this case it's polymethyl methacrylate, which is a plastic you use often in your daily life, and a lot of your glasses actually is made of polymethyl methacrylate. You just covalent link those two chains together, and magic happens. Okay, so polystyrene does not like polymethyl methacrylate, just like water doesn't like oil, so they tend to feel separate. But because they are covalent linked together, they are brothers and sisters, they really couldn't go too far away, and they end up with a range of beautiful nanostructures. Okay, and by controlling the fraction of each individual component, you can go from sphere, cylinder, lamellae, or to gyroid. Even more morphology is very sophisticated. And the beauty of this is that you get it for free. Okay, so many of you probably working with lithography. Whether you use E-beam lithography or UV lithography. And especially if you work with E-beam lithography, you will see that you can get very well controlled pattern, but it's painstaking. Okay, so if you want to do 1 millimeter by 1 millimeter, it can take a fairly long time. But in other things that if you use lithography, the dimension you get probably is going to be hard to go below 35 nanometer reliably. But in the case of here, you can easily tailor the dimension of individual structures by tailoring the size, the dimension of your polymer chain. And it's easily getting itself into like 10 to 100 nanometer range. And that is really the sweet spot. And just for a reference that we were talking about, if you look at my hair, the diameter of my hair is about 40 micrometers. So that's about 3 order magnitude bigger than what we were talking about here. Okay, so how are you going to use it? It's very simple. I call it just like baking a cake. You have a polymer, and then you just dissolve in solvent. Oftentimes, those are organic solvent. And then you spin cast it, just like making a crepe. You put it on, and you put it put it on a substrate, and you let it spin. Okay, and the solvent evaporate, you're going to have a smooth, thin film which controls thickness on it. And then subsequently, just put it in the oven or put it under the solvent, give the polymer a little bit mobility so they can do their own magic, start to self-assemble. And then what you see is using cylinder forming block copolymer as example, you can see is that the cylinders either laying parallel to the surface or they can standing normal to the surface. Okay, and in the case when you have cylinders standing normal to the surface, you can see that polymethyl methacrylate actually can be used as a photoresist. So if you shine UV light on it, I can chop it up and then substrate gets selected and removed. And then what you're going to get is styrofoam. But the only thing is that in this case, it's nanostructured styrofoam film. So what's showing you here is FESEM. Okay, it's a field emission scanning electron microscope image. So here's a substrate, and scale bar is 100 nanometers, and the film is about 30 nanometer thick. We can see is that within field of view, what you see is a honeycomb. You have about 15 nanometer pores, hexagonal packed. Okay, the pores go all the way into the bottom, and this can go as large area as you want it. Okay, if you have a large enough spin coater, you can make it as large as the room. There's no size limit. Okay, so once you have this nanostructured styrofoam, what are you going to do with it? Okay, so there are many things. You can use this as a mask for template transfer. Okay, you can control the etching rate as well as the etching ratio, and transfer in this case is silicon. Okay, or you can couple with the lithography technique and then subsequently manufacture the devices you would like to have. Okay, in this case is we deposit a whole bunch of a cobalt nanowire in there that would measure the magnetic property of the device. Each individual pores can also be used as nanoreactor. Okay, you can do chemistry in the confined geometry. And in this case, you can grow silicon oxide into each individual reactor, and subsequently, actually, the matrix got removed. And what you see is glass pillar, hexagonal pack. They have really good fidelity to the template. Or if you're in the biotech company, a lot of things goes into how you can separate things with very sharp size cutoff. And you can put this as a coating to the commercial filter. Okay, and then depends on the pore size, you'll be able to do this separation based on the size. And in this case, actually, you can easily separate the virus particles. So 15 nanometer is in the good size range of the size of the virus particles. You can do virus particle purification fairly easily. Or alternatively, what you can do is you can deposit a cobalt nanowire in there. And then as you start to control the aspect ratio of the cobalt nanowire, you can actually use each individual of them as a storage. Okay? So in this case, you can imagine that if you look at this nanostructured styrofoam, you can see that it's going to be hard for me to use this for memory storage because I need to have a reader and a writer, read and write head on it. So namely, I need to write the information into this individual wire, and then I need to come back to read it. Okay? And what that said is that, many of you see the disk, you see that the reader need to be, you set in one place, you say, okay, that's a nanowire, you need to know where it is. Then, a centimeter away, you need to know if you land on a matrix or you land on a wire, and that's very important. However, if you look at here, you see that my green size is fairly small. Locally, they are hexagonal packed, but the long-range order is very poor. So it's impossible for me to predict where I'm going to be at a centimeter away from that particular spot, which requires to control the long-range order of this nanostructure. Okay, so this is just show you a couple examples, just without even control the long range order, what you can do. Okay, so this is one product come out at 2003 from IBM, and this is another. They had a news release at 2007, just using exact the same technology, and they even bothered to change the polymer. It's polystyrene polymer macroscopic. Everything is exactly the same as what I did when I was a graduate student, and of course I was in a big team. Okay, so we talk about how to control the long range order, and then what you see is that initially this was published in 2003 or 2004 in Advanced Material. So at that time, what we're trying to see is that if there is any way how to improve the long range order of the system. Okay, so I know my block copolymer is going to allow us to generate locally hexagonal packed cylinders. And if we start to couple that with the lithography pattern, the surface, namely you put down the trenches in the sample on your substrate, and then what you get is that within each individual trenches, you actually can use the wall to guide the growth of the grain. And in this case, you can see this is 6 micron scan, and then you see there are certain registry in between different rows. Okay, so you get, if you do a Fourier transform of this AFM image, you essentially get hexagonal packed spot. Okay, indicating that the whole image are, essentially one grain. This was okay, and actually, Toshiba has been using this type of similar technique using cylindrical forming block copolymer for memory storage. But every time you start using lithography pattern surface first and then coupled with block copolymer, it's a two-step process. Also, you lose the reality. You lose your real estate. Okay, you always tend to lose the areas which you can pack into the system, and it just with the size you are looking into, an ideal case will be, can I do everything in one shot with a very simple way, and then not limited by how large area my lithography pattern surface may be. So we work with Professor Tom Russell at the University of Massachusetts Amherst for about 2 years, for about a year till the paper was published. And essentially we're looking to see what are available. How can we start to walk away from this lithography pattern surface, but use something that is very simple, okay? So we'll go back, we say, if you look at the silicon wafer, our people grow the silicon, 18-inch wafer is not a big deal. And if you look at that wafer, the whole wafer is essentially single crystal. They're atomic with registry to each other, okay? So if we can translate the atomically ordered single crystal of the inorganic material and use those to guide the assembly of block copolymer, then we should be able to get this microscopic aligned, microdomain with large order. Okay, but the question here is that if you look at inorganic material, they're atomically registered. Okay, and the polymer microdomain typically can be like 10 to 100 nanometers. You have like a 1 or 2 order difference between those two. Okay, how you can translate this atomically ordered single crystal to a few nanometer or tens of nanometer ordered into the block copolymer microdomain. Okay, so we'll look at it, what we'll see is that there are things readily available, because if you miscut a crystal, okay, and the crystal at a certain angle, the crystal, and then you re-anneal it, the crystal is going to generate this sawtooth pattern, okay, and this angle is going to be dictated by the crystal plane of this inorganic material. Okay, if that's the case, what I'm going to have is that in the microscopic distance, you see the ridges or the sawtooth pattern should go in one direction, and that direction should be dictated by the crystal growth. And if you can get a very large crystal, I will be easily put that, get into the trenches order toward one direction. So we went to a lab, we tried it, and it turned out to be really good. Okay, we were using sapphire as an example. Okay, this is AFM image of a miscut sapphire. It's fairly smooth. You heat it, you bake it at about 1300 degrees, and what do you see under AFM image? You can see the different, ridges come out. Okay, we call it a sawtooth pattern. And what interesting is that you see the pattern goes into one direction. Okay, if you scan in any area, so we do like an inch by inch, the inch square size of the sapphire, you can see it can be in anywhere you scan, they are going to be with registry to each other. Okay, the whole idea is that then subsequently you have your polymer in there. The polymer, how the polymer is going to order, is going to be biased by the substrate underlying. And if you select the pitch and select the periodicity in between the trench properly to match what you see in the polymer, you should be able to direct the polymer assembly over a microscopic distance. Okay, so these are a series of AFM image, and this is one sapphire substrate and with a certain frequency, with a certain periodicity. And then those are two different polymers with different molecular weight. You can see in this case, I can easily tailor the spacing as well as the feature size, but just changing the molecular weight I have. And again, I can also just take another substrate and then you have different spacing in there. And what the take-home message is that for all the samples we look at it, you can see they have hexagonal packed with really good long-range order. And if you do image analysis, the translational order is also fairly good. Okay, and then what I want to bring to your attention is that in this case that the interdistance between the cylindrical microdomain is about 7 nanometers, and that is fairly small. Okay, so in order to make sure that you do AFM, you do like a micron, maybe sometimes you can do 2 micron, maybe even 10 micron scale. But it's really hard to convince people saying that I'm having the whole substrate have all the cylinders aligned in one direction, all the grains grow in one direction. So to that, we do grazing incident small angle X-ray scattering. Okay, what is it? So in this case, this is my substrate. Okay, and I'm bringing an X-ray beam at a very shallow angle. Okay, if I shine an X-ray beam onto the surface at a very shallow angle, and the X-ray is going to bounce off the surface, and it's going to carry the information of the ordering inside of the film. Okay, and you can imagine that the beam has a certain width, in this case about 20 to 50 micrometers. And by the time you do at the 0.1 or 0.2 degrees, the spread of the beam, or we call it footprint, on the sample can go into like a centimeter, 1 or 2 centimeter in distance. What that said is that what you are collecting here in your detector is going to reflect the ordering information for the areas that you are looking at, which is about centimeter to 2 centimeter area. So that is going to allow us to probe what is the ordering of the block of polymer in a large distance. Okay, so you need to follow with me a little bit. So we line up the sample with respect to the beam. Okay, so if the cylinders are hexagonal, look at from the top. Okay, if they are all aligned with this, okay, what I'm going to see is 1 to 2 to 3. Okay, so essentially I'm seeing lines of the cylinders line up. Okay, so if you look at the ratio, we'll go like 1, 2, 3, 4, 5, 6. Okay, you don't see other planes. Okay, and then as you start to tilt another 60 degrees. Okay, and then what you're going to see is going to have like hexagon packed, and you look at another plane, and if you go back to rotate another 60 degrees, another 6 degrees, and then you see this scattering pattern coming back. So the whole take-home message is that within the area the beam is sampling, which is about 1 centimeter to 2 centimeters, all the cylinders need to be oriented in one direction. Okay, otherwise you are going to see a mixture of hexagonal, with hexagonal grains start to rotate. You're going to see 1 over square root 3 over 2, and you wouldn't see this clean diffraction pattern of the sample. Okay, so the next question is coming down to is that as you start to look into the inorganic, single crystal substrate, oftentimes that as you start to do the miscut and then they start to reconstruct, they are going to form defects. Okay, and it turned out that actually was a concern in the beginning, but it turned out that polymer can fix that. Okay, so they're self-correcting. Okay, so in this case, this is AFM image. We scratch off the film. So in this side, you can see the film is still on, and this side is scratched off, and then you see the underlying sawtooth pattern of the substrate. Okay, and then you can just also look at the AFM image on the top, and to look at the correlation between the defect in your underlying substrate versus the top of the surface ordering of the block of polymer. Okay, so in this picture, essentially we circle all the defects. You can see there are a lot of it. The density of the defects is fairly high. But if you look at the top of the polymers, they are hexagonal packed with really good large order. So what this said is that even though the underlying substrate have a defect, and the defect density can be fairly high, but by coupling the single crystal of the inorganic material together with a self-assembled block of polymers, you can indeed generate this nanostructured thin film membrane or thin block of polymer thin film with really good large order. Okay, and this is, by reducing the molecular weight, you can actually generate features as small as 3 nanometers, and that translates to 10.5 terabit inch square. And if you look at this versus Moore's law, we are about a 1 to 2 order magnitude higher than what the current state of art. And on the other side is that because it's so dense, it cannot be read and write. The current technology cannot really take advantages of the templating we can provide. So if any of you are interested in working in this area, that'd be great. Okay, so with that, I told you the first part is how can we control the template, okay, which can be used as mask or scaffold for nanodevices subsequently. Okay, so this cartoon essentially saying that we can set up this structure frame, which is labeled as nanometer here. Okay, we are also interested to see can we incorporate the building functionality directly instead of trying to do this post modification. Okay, and in particular, we are interested in this particular area. We're interested in the electronic, magnetic, optical properties, as well as biological. How can we interface with biological system and be able to communicate at the molecular level? So my group has been working on, I'm just going to give you a flavor of a few areas we're working on. One is that we're trying to use block of polymer to direct nanoparticle assembly. Many of you probably are working on nanoparticles, and they are very unique. They sort of serve as the interface between the soft material and the hard materials. And then they certainly have a lot of applications. And right now, many things come down to is that can you control the nanoparticle ordering? Okay, can you control the interparticle distance? Can you control what you have in the periphery of the particles? And one example you look at is for the energy harvesting or storage, is 2 different areas that has been, work. There are a lot of exciting work come out. In the case of if you want to use nanoparticle for the hybrid photovoltaic, okay, you need to get the particle lined up with a certain orientations, with a certain interparticle electronic communication. And in the case of the storage, if you want to use it as a capacitor, okay, you wanted to control the dielectric properties of your nanoparticles, of your nanocomposite, which is come down to, reduced down to the special distribution of the particle as well as interparticle ordering, okay? And of course, there's many, many other possible applications. If you're just going to the, any particular journal, open up, it's just all over the place, okay? So we are not the first one working on trying to direct nanoparticle assembly using block of polymer. A lot of people have done it, and I showed you a few examples here. You can see that the particles are microscopically assembled, but overall, the optimization of the particle ordering required to be, need to be improved. Okay, so what we are interested in is that we really don't want to modify the particle. We want to use particle as is they are synthesized. Many of you probably work with using nanoparticle as a sensor. Okay, so essentially when you have changed the ligand on the particle, you actually can change the optical property of the particle. Of course, if you look at lead sulfide, again, what is on the ligand can easily change it from N-type to P-type. So in order to maintain building functionality, we wanted to just use particle as is, okay, not to pass around with it. Okay, of course, I told you that controlling the interparticle ordering is important. Okay, and what we really wanted to do is to make responsive nanocomposites. Okay, that will allow us to tailor the microscopic property of nanocomposite using external stimuli. Essentially, you put a hand that can potentially go into the system, try to massage the particle, and to give you the proper property you want to have. Okay, and the system we use can be described here. Essentially, is that instead of using a block copolymer, which has been challenging to be able to control the interparticle ordering, and actually oftentimes require the particle modification, we actually put a small molecule which is added as mediator. Okay, and this is one of the TEM tomography showing you that indeed we can incorporate the nanoparticle into the block copolymer with assistance from the small molecule, and you can see that it forms lines and form sheets of them. Okay. And if you look at the TEM image, want to see how nice you can control the particle ordering. This is just a cross-section of the TEM image. You can see that the particle is only one particle in width. Okay, you only have this one sheet of nanoparticle in the system. And if you do a TEM image analysis, what you see is essentially average out the density, electron density, when you average out the sample, and this is what you have. Essentially, for a 4 nanometer nanoparticles, the full width at half maximum is about 6.62 nanometer, which means you can control the spatial distribution of the nanoparticle within a fraction of the one single particle size, and that is pretty nice. And of course, one advantage we have with block copolymer is that you can easily control the morphology. Okay, so by changing from a lamellae forming polymer into a cylindrical microdomain forming polymers, you can see that the particle actually can easily form a hexagon array. Okay, and of course, there are a lot of unique optical properties may arise from that. Okay, and this is just to show you again the TEM tomography of, you can see this beautiful honeycomb made of nanoparticles. All right, so I mentioned to you earlier that we would like to have a hand going to massage the particle, okay? Ideally, we would like to have the particle to be either connected or separated apart, okay? And in the case of optical properties, we also would like to change the spacing between the particle assembly, okay? If you look at reflect index, and that is going to change the wavelengths, what we are going to get the optical property coming out. Okay, so in this case, by changing the property of the small molecule we're using, we actually can easily tailor between those 3 different morphologies in a controlled manner. Okay, in this case, the particle from the particle assembly distance about 34 nanometers, and in this case about 15, and in this case you go back to like 25. You can clearly see that the interparticle coupling is going to change. Okay, and if we monitor it with in situ small X-ray scattering, and what I want to show you here is that the peaks more or less reflect the spatial distribution of the particle within the composite. And you can see that the peak goes up and then go down, and then it goes up again. And the whole process only takes about a few minutes, which means that you can indeed control the particle, trying to take the particle as a little golf balls, right? You can just flip it and then change it to whichever way you would like to get, okay? And what are other things we would like to do, okay? By using a light-responsive nanoparticles, a small molecule in there, we also wanted to use the light to be able to control the interparticle ordering. And that's exactly what we did. This is azobenzene containing small molecules, and by shining UV light on it. So this is in the trans state, and then we can go to a cis state. So actually this ring is going to flip up, okay, form this type of a cis transformation. As a small molecule change its conformation, the particle is going to be drive around. And that's what you see here. You look at the small angle X-ray scattering, essentially tell you the particle spectral distribution. That's what you see. You go from trans to cis, and then you can actually go back to trans again. Okay, so the process is again, it's reversible. But overall, what this said is that you can indeed using light to control the particle assembly within the nanocomposite. Okay, so we're not done there yet. We'll show you what's going on in the bulk. Many nano devices is fabricated using thin film geometry. And in thin film, it's important to control the particle microscopic alignment. Okay, in the beginning of the talk, I told you about this, nanostructured styrofoam. The cylinders is standing normal to the surface. And for many other applications, you would like to have the particle laying parallel to the surface. Can you control that? Okay, so the take-home message, indeed we can. In this case, this is essential. It's a layer of nanoparticle laying parallel to the surface, and this is in the case the particle is standing normal to the surface. And then you see that in this case, why the particle is not aligned strictly. Okay, that's the straight. But the straight is you want to get. The whole reason is that because in this case, the lamellae, they sort of turn around back and forth, and based on the study, I showed you that with the lithography pattern surface, you should be able to easily straighten it, make it, go straight. But this, if you can do this, you should be able to directly using pattern surface to get them to line up into the pattern you would like to have. Okay, so last 3 minutes, I'm going to just tell you some of the work that how you can incorporate biological functionality into your system, but control the nanostructure and trying to be able to enhance to generate biomolecular functional materials. One area my group is working on is trying to mimic transmembrane proteins. Okay, and in this case, you can see it can do a transport, you can be enzymatic reactor, and it can also be a signaling process. And we all know how great nature can be, and we all know the distance between the synthetic material to be able to make materials that are comparable to what you see in nature. But in this case, we're trying to combine it together. Okay, so what we're interested in looking at is that to take out a fragment or subunit of functional motif from natural system and couple it together with a block copolymer. Okay, so again, by using the block copolymer self-assemble to specially distribute the biological motif in a controlled manner, and then within it take advantage of the biological. In this case, we're interested in both light-induced light charge separation and electron transfer, as well as enzymatic reactor. Okay, so this is from the cofactor to the peptide, and then to co-assemble it with block copolymers. Okay, and basically the take-home message is that even though those two systems are fairly remote from each other, one is synthetic, the other biological, what we can do is we can also order them into a very high density array. And most important, what we get is that we are not losing any of the activity of the enzyme. In this case, we use horseradish peroxide, and we can still have, in this, you can probably see a little silicon wafer in there, and that's the substrate encapsulate this enzyme in there. And at very low concentration of the enzyme, we'll be able to get activity. Okay, so with that, I would like to conclude my talk today. So I told you some of the work we have done trying to control the lateral ordering of block copolymer in order to generate a porous template for nano device or for the pattern transfer. Told you some of the work is ongoing in my group trying to look at a small molecule directed nanoparticle assembly, and there has been a lot of new things come up, and there's this particular project have a lot of potential to help out building nano devices. And I only briefly tell you some work trying to interface synthetic material with biological system and trying to generate biomolecular materials. Okay, and with that, I would like to thank you for your attention, and I'm happy to answer questions.
Does anyone have any questions right now? Okay.
Hi, I was curious how the nanopores in the polystyrene polymethyl methacrylate responded to high temperatures.
And they are stable up to about 100 degrees. That's related to the glass transition temperature of the polymers.
Thank you.
Yes, but you actually, if you want to have, you can use that as template to do the mineralization. You can actually grow silicon oxide or even titanium oxide using polymer as a matrix. Okay, then you maintain your structure in the inorganic structure frame. Alternatively, what you can do is you can use them as an etching mask, and if you control the etching condition right, you can easily get porous silicon or some other type of inorganic material with a fairly high aspect ratio. I would say 1 to 10 is not something out of question.
Do you have any other questions? Oh, here.
Hello. I was wondering, so you showed a lot of kind of these nanoparticles arranging in matrix type shapes, but are you able to make closed shapes like a buckyball almost, or kind of like a cage using your particles and telling them to self-assemble in an encapsulating shape?
I think it's possible. We haven't made it yet, but theoretically there shouldn't be difficult there, because what we can do, we can use a spherical forming nanoparticle and sequester spherical forming block of polymer and sequester nanoparticle right at the interface. Okay, and then you have the polymer fitting the core, and then you have the particle fitting at the interface. But we haven't done that yet.
Oh, yeah. Thank you.
Okay. Oh, one more question here.
Let's see. Many of today's attendees are not chemical specialists, probably kind of E guys. So the questions are, what's a possible involvement and contribution to your subject from E guys?
Oh, okay. So actually, we really need help. We can make these beautiful structures, and from the first part, it's very clear that we can easily interface and to generate for the device fabrication. We don't have a barrier there. And we would like to test. And the other thing is that, especially with the nanoparticle project, we are not limited to the particle type. So we can do semiconductor, and we can do magnetic. We can also do metallic nanoparticles, and the particles with plasmonic properties. And we are actually not limited by the particle size and the shape either. So right now, for us, we really wanted to know what do you guys want to do, and what we can make for you guys. I'm interested in the optical properties because of the unique optical property built into the nanoparticles. I'm interested in looking at when you have semiconductor particles, how the particle contribution is going to be. My group is in the process of looking at the dielectric constant of the nanocomposite by controlling the nanoparticle assembly, as well as both at the interparticle ordering as well as at the interface. So there's a lot of interesting area can potentially be done, but I have limited resources, and this is really going out of my comfort zone to look at, to fabricate device, and I would like to have collaborations with experts. So.
Okay, I think thank you so much for a great talk.